Good morning, good evening. Hello, everybody, for tuning in to our second presentation of the day. I'm delighted to introduce Nouhad Bachnak, who is the managing director of the Swiss branch of Sunway Communication, and he will share some insights about their 3D plating, 3D packaging, and 3D MID technologies at Sunway Communication. And with that, Nouhad, over to you.
Thank you, Christoph, for the introduction, and welcome everybody to my presentation about 3D plating, 3D packaging, and 3D MID. To who is not familiar with the abbreviation MID, this is molded interconnect devices or newly mechatronic integrated device. Yeah. So, first an overview about Sunway Communication, just 2 slides presenting the company. Then something about the variety of selective plating technologies used at Sunway in order to create 2D or 3D circuits. Then I will present a new process. We call it LSCA. This stands for laser structuring chemical activation. I will present this process and its capabilities. This is a process, new process in development, and I will show some application examples. And at the end, what's very important, everything which is not reliable, you can't use it. We have achieved a high reliability regarding plating on plastic substrates. And I will show one slide showing these capabilities about robustness and costs. Sunway Communication is a Chinese company based in Shenzhen. We have more than 10,000 employees worldwide. We have a revenue of more than $1 billion per year. Hence, we are in nearly every industry. We have all this quality certification, for example, for medical, for automotive, and so on. We invest heavily in research and development, about 9% of our revenue. And in terms of innovation, we have more than 1,500 patents. And according to a UL study, Sunway Communication is on the third place in terms of granted patents for 5G antennas. The production and the main activities are in China. Nevertheless, we have overall in the world, we have facilities, mainly research and development. So production in China, research and development, customer support, marketing, project acquisition in Japan, Korea, USA. In Europe, we are located in Sweden, the headquarter, and in Switzerland, this is where I am located. And here in Switzerland, we are dealing mainly with 3D MID, or in general, with 3D plating on different substrates, I would say, not only plastic. Here to show you a snapshot of our products. So it's a big variety of components and modules. I will not present them all. We will concentrate today on plating technologies in order to create 3D circuits, 3D substrates, and we call it 3D MID. Technology in general, there are many processes, and the main topic will be this LSCA process. So here's a variety of plating technologies we use at Sunway. Plating on plastic, everybody know that, maybe two-shot molding. There's two processes, LDS and LSCA. I will explain it a little bit more to who is not familiar with that. LDS means laser direct structuring, and actually it's a very good established process now, mainly for antennas, or it started with antennas, but in the meantime, we have applications everywhere, whether it's automotive, consumer, medical. How it works? So you have a 3D substrate, thermoplast. using a laser, you structure, let's say, the circuit you need on this 3D substrate, and then using chemical plating, you plate this structure. So you have the circuit in 3D format, actually. The other processes, they are similar. LSS is like LDS, but it works the other way. So you don't structure a 3D circuit on a plastic. You plate the whole plastic, then you remove the metal where you don't need actually, and so you create the structure. LEP is laser activation plating. There are all names actually. You use a laser also, but the activation is not in the plastic. You have to add the activation from the outside. The LDS material, you need an additive. This additive is based on kappa complex, and with the laser actually adding heat to the plastic, you make it rough. You structure the plastic part, and you activate this metal complex inside. So the LAP, you don't need this additive inside, but you always need activation to be able to put metal, or it's actually copper on the plastic. So you need an activation. This is based on palladium normally. The second process is similar to LAP, but here we use another chemical. It's not palladium in order to activate the plastic. And I will explain it a little bit more later. And there are other plating technologies like PVD or photolithography or electroplating. Here explaining the LSCA process. LSCA stands for laser extraction chemical activation. This is a new process where we don't need this additive inside of the material. So the LDS process is the most used process now. We have about 80 to 90% of the projects in 3D MID we do with this process. But here you need this additive inside. Let's say if you need a transparent material and you add this additive, this will be not transparent anymore. Or if you have a biocompatible material and you add this additive in order to be able to structure and plate it, this will be not biocompatible anymore. So we started to look for solutions where we can use a broader range of materials because we can't add this LDS additive to every material. At the beginning, actually, we have achieved good results with a process where we use the same setup of laser parameters we used for the LDS, but this works only for a small variety of materials. And we have worked with other partners, let's say, where we have now very broad variety of substrates. We can plate on plastic, on glass, on ceramic, on thermoplastic, and so on. So how this process works, you see on the right side the laser structuring. Actually, you have a value scanner where you can adjust the z-axis, and here, if you can see the cursor, here there's the value scanner, and here are mirrors where you can manipulate the laser beam in the XY direction. So in a certain working area, you can structure a completely 3D part. Additionally, you can use mechanical axis to turn the part to structure it from every side. So this is the laser structure. Then chemical activation, and the rest is chemical copper, chemical nickel, chemical gold. This is the standard process. So the differentiation between the LDS now and the new developed process is actually in the laser structuring and in the chemical activation. Laser structuring, I have mentioned, using the same laser parameter setup, works for certain materials, but not for all. And with the new laser development, we are able to also structure glass and ceramic and plastic thermosets also. And the second one is the kind of activation. This is not the standard palladium activation. This is not the additive which is in the LDS material. This is a specific chemical mix to activate this structure, even though you don't have any additive inside of the plastic. And the activation is only for the structure and not for the whole plastic part. Otherwise, you will not have any selectivity. So this is the main idea how this process works. Now we have compared not with all the, let's say, processes, but the main known processes, LDS, LEP. PVD actually is not 3D process, but we have seen that we can use this process also for flat substrates. Therefore, we put PVD here for comparison. As you can see, with if you compare the LSCA process to LDS and LEP, it's superior in terms of plating on more substrates. If you compare this process with PVD, you can plate on a high variety of substrate, but you can't do 3D shapes, and the production costs are high. So comparing this process with many other processes, I would say that it's not just an improvement, it's really a disruptive technological leap, because in terms of lines spacing, we go down from 100 to 200 micrometer, or here I write 80 micrometer in the standard LDS process, the standard MID, down to 5 micron. In terms of 3D, if we compare that with PVD, this is really full 3D. And in terms of cost also, it's a very easy process, just laser structuring without adding anything, activation and plating. Here are the capabilities I have mentioned already. We can do structure on nearly every material. I have presented here thermoset, glass, PET, and ceramics, some examples where we can use it. And additionally, the surface roughness is very low. This is good, for example, for antennas. And the width of the traces can go down to 5 micron. This is very interesting. The 5 microns, maybe you don't need it if you create a circuit, but if you want to create an invisible circuit or invisible lines, the normal eye can see everything higher than uh, me not, maybe 10 micron, but I mean, so if you can see very good, lower than 5 micron, you can see it anymore. So you can create invisible circuit also. The diameter proven for 40 micron, but it can be done for lower than 40 micron. And the typical plating, copper, nickel, gold. Actually, we have to start with the copper layer. Nickel, gold, this can be also something other, let's say tin or silver, but the standard plating is copper, nickel, gold. Here on the right side, two pictures. This is plating on biocompatible materials without any additive inside, and the other one plating on glass. Application examples, three of those application examples. On the left side, you see capability to make thin lines, allow us to use 3D MID on the IC substrates. And the next picture is circuit on glass with even through-hole plating. And the third one is maybe future technology. I have mentioned below 5 micron, the normal eye can't see the structure anymore. Here for all the touch screen, you need a conductive layer. Normally it's ITU, indium thin oxide. If we structure, let's say, a grid of copper, we will achieve the same function without, let's say, you can see it. There is a grid, but you can see it, but you have the touch screen function. Here another example where we show the use of 3D MID for 3D packaging. If you have the standard packaging, you have a die, you need a substrate, normally a PCB or lead frame, and you have to attach this die to the PCB via wire bonding or via flip chip. And additionally, you need also balls or pins or whatever to connect this die to another PCB. So, and you need the housing, you have to mold it in order to make the package. Using 3D MID, whether this LSCA process or another process, but the LSCA, you can go down with traces to, let's say, 20, 10 micron, even 5 micron. You can create the housing. You put the structure directly on the housing, and even if you look here on the right side, even the connection between the inner side of the housing and the outer side uh, can be created um, in one part by injection molding. So we have only to connect then the chip, the die, to the structure, to the circuit. So this can be done with bonding, wire bonding, or with the flip chip, the same technology like PCB. But here we have the whole housing, the whole connection, whether pins or balls in one part, and this housing serves as, let's say, yeah, you have to overmold it, and it's done. So at the end, the most important one, everything which is not reliable for mass production or can't withstand environmental tests is fine. You do something in the laboratory, but you can't use it. Here we have developed a plating process. So, I mean, you have the structure, you have the activation, now you plate. And normally use different substrates. Glass, plastic, ceramics, whatever. So, and on top you have copper nickel gold. And substrates which expand very fast or due to temperature or due to humidity, they will expand faster than the plating. And then we will have cracks or delimitation of the parts. We faced such issues, I would say, 6 years ago, and we have worked on a plating process where we have developed a specific plating process for plastic materials where we can withstand all the tests, automotive tests, with more than 1,000 hours, especially the humidity and the temperature test. Yeah, for industrial consumer goods, the requirement was 90 degree at 65, 90 relative humidity at 65 degrees, 72 hours. And 6 years ago, we had one application where we faced some issues and started to develop this process. And we have achieved now more than 1,000 hour. Internal tests which were done were at 90 degrees and 90 relative humidity. Without any issues. Actually, after 500 hours, I would say the part is expands enough, and nothing will happen. We have achieved 1,000 hours without any cracks, without any diminution. So bondability is very interesting if you want to use it for 3D packaging, because this laser structuring makes the surface a little bit rough. And the roughness of the surface with normal, I would say, laser structuring LDS is about 20, 30 micron. So, and the wire, if you use a 25 micron wire, so the diameter of the wire is smaller than the roughness. And if you have wedge bonding, for example, you will cut the wire before you bond it because of the high roughness. And here we have developed surfaces where we have lower than 10 microns, so lower than the radius of the bonding wire. We don't need any pre-treatment for that. It's done from the beginning. So it's a combination of laser structuring and plating where we can achieve such roughnesses where we don't need any pre-treatment for the surface. And regarding cost, this plating process we have developed, actually normally you think if you develop something, that you will develop it at the cost of something else. So is rarely that you can achieve better technical characteristic and lower cost, but indeed this process is less expensive than the standard process, this plating process. Here I show some applications. On the first one, for example, this is a part where we have holes inside, and this is done by LCP material. And you know, LCP, if you have holes, you will have welding line, and if you plate over welding line, this is you may have cracks. With this process, we can plate over welding line without having any cracks. The second one is a part where we have more than 7 meter long um, lines or structure with a very fine pitch. It's three-dimensional. The material is PA. It absorbs a lot of humidity without any cracks. And the third one to show the bonding capabilities. So this is my presentation. Thank you for your attention. If you have any question, I am ready to answer all your questions.
Thank you very much, Nuho.